Okay, so we've been talking obviously about organic chemistry, and we got into alkenes and alkynes. Remember that alkene sort of functional group is carbon-carbon double bond, where alkyne is the carbon-carbon triple bond, is basically sort of the functional group for it. Remember that when we name pretty much anything that's sort of organic, what we're aiming for in terms of sort of identifying the name and sort of figuring out the name is we always want to find the longest continuous carbon chain. And the important part of that is that the longest continuous carbon chain does contain the actual functional group. So the functional group, so for example, double bond needs to be in the longest continuous carbon chain. A triple bond there needs to be in that longest continuous carbon chain that you count. And they're all based off of those first 10 alkanes as we've been seeing. So again, really important as we've been talking about to make sure that you get a handle on those names of the first 10 alkanes. Pretty much everything falls back to those guys. How do we change the name? Well, an alkene, ENE, is when we have a double bond. So we insert that in place of the ANE for our alkane name. Our alkyne, YNE, gets replaced there of the ANE in our alkane name. Also different a couple things when we number for an alkane. It is usually the groups that are important in terms of which way we number that chain. We want to number it to give the groups the smallest number. When we now start to move into double bonds and triple bonds, we want to number whichever way gives the double bond or triple bond actually the smaller number. So the sort of functional group does take the priority in terms of numbering. Once we decide which way we're numbering it based on the double bond or triple bond, any other group that's there is numbered accordingly. So they're numbered accordingly to how you decided either really left to right or right to left in terms of your numbering approach. The other different thing as well is with a double bond or a triple bond, we do need to give the location of where we find the double bond or triple bond when there's a kind of more than one option for where it could be. That usually occurs about, 4 or more carbons, and we add that to the name as well. All right, so I think we did some examples there at the end. Let's just do a couple more just to make sure. So let us go with, why don't you, if I could get my thing to right here. There we go. All right, so why don't we go with this guy here. And throw one of those guys up there. And why don't we also go with this guy here. All right, so why don't you take a couple of minutes here and give the proper IUPAC name there. Remember, the IUPAC name is kind of like the official name there that we've been talking about. So take a moment or two and see what you come up with. Okay, so let's take a look and see. So remember, we're looking for always the longest continuous carbon chain that contains the functional groups. So if we just go kind of straight, 1, 2, 3, 4, 5, 6, 7, if we went up. We could also go 1, 2, 3, 4, 5, 6, 7, gives us 7. Could also go 1, 2, 3, 4, 5, 6, 7. Could also go 1, 2, 3, 4, 5, 6, 7. So it looks like 7 is the winner here, no matter sort of which way we go. Take the straightest sort of 7 you could do, obviously coming this way, and then you could choose up or down. So I'll just go up. Why not? Go this way. So that is going to be, again, the basis of our name here. So I believe I counted 7 there. 7 is based off of heptane because we have a double bond happening there. Heptane becomes heptene. We now, no, I believe there's 7. So there's 1, unless I miscounted, 2, 3, 4. There's 1 hiding right here. 5.
Oh yeah, that's the one.
6. Yep. Other questions on that? So 7 again, based off of heptane, because of the double bond, becomes heptene. And at this point, we got a couple of groups hanging out. We got this 2 carbon group here, which would be based off of ethane, which would be an ethyl group. We got our 1 carbon group over here, which is based off of methane, which would be a methyl group. And that means what is left to do is to number our chain. Remember that in this case, because there's that double bond, which is the functional group, we're looking to give it the smallest number. So going right to left here will probably accomplish that. Again, not skipping that guy there. 3, 4, 5, 6, and 7. Again, if you kind of go the other way, you can kind of just see it. 1, 2, 3, 4. Obviously, going right to left gives our double bond carbon 3. Going left to right gives our double bond carbon 4. So we would want, in this case, to go right to left again because it is the smaller number, which is always what we're shooting for in terms of our double bond. Any questions on that? That means our double bonds at carbon number 3, which is why we would then put 3-heptene. 3, again, the location of where our double bond is at. At this point here, we just need to give our groups here. So because we locked in this numbering for our double bond, that means that the ethyl group ends up at carbon number 3, and my methyl group ends up at carbon number 6. So here we will end up with alphabetical E before N. That's right, that's alphabetical, I think. So this will be something like 3-ethyl, 6-methyl, 3-heptene. Any questions on that particular name there? Looking at our second one, we can kind of see, since there's really no branching happening of carbons, our longest carbon chain is just going to be straight across pretty much. And in this case, if we count up what we got going there, we've got 1, 2, 3, 4, 5, 6 carbons. So 6 carbons, again, based off of hexane, because in this case we have a triple bond, makes it an alkyne, and it becomes hexyne, Y-N-E at the end. Going left to right, in terms of our numbering, puts our triple bond at carbon number 3. Going right to left puts our triple bond at carbon number 3. So clearly, no matter which way we go, carbon number 3 is where our triple bond is. So which way should we actually go in this case? So because the functional group here is tied, what would be the next important thing in terms of the name? The next important thing in terms of the name would be the group that's attached. So because it does not make a difference which way you go for our triple bond, which is really the most important thing here, we're going to actually choose the top numbering, left to right, because in the top numbering, that gives our group, which is the bromine or the bromol group, a smaller number than if we went right to left. So instead of 5 bromol, we now have 2 bromol. Putting that together with the rest of the name there gives us 2 bromol, 3 hexyne. Question on those names there?
Okay, just to make clear, let me see. So when we are looking at the carbon chain, if it
Mhm.
has a double bond, we want to make that the shortest bond before we take a look at the functional groups that are attached to it.
So the actual double bond or triple bond would actually be the functional group.
Okay.
The other groups are what are referred to as alkyl groups. They're substituents, which basically means in the situation of either the double bond or the triple bond, the double bond or the triple bond is pretty much the functional group that makes it like an alkene or an alkyne because the presence of the double bond or triple bond. So that's sort of the most important thing in terms of everything, in terms of the classification of it. And that's why when we would number, we would look at the double bond versus our triple bond first and try to give it the smaller number rather than the groups that's attached. Um, we didn't do that with the alkanes because technically speaking, the functional group for an alkane is the carbon-carbon single bond. But because everything's basically a single bond and all organic sort of guys, basically, the most important thing in an alkane is actually where the groups are attached. But as we move away from alkanes and get into alkenes, alkynes, alcohols, everything else that's sort of different organic functional groups, it's always the functional groups that's the most important and always gets the priority in terms of how you number the sort of chain. And then if that happens to be a tie like it was on the bottom here, then you want to go to kind of what the next important thing would be. And the next important thing would then be to try to get your groups to the smaller number. And we could do that on the bottom one because it didn't matter which way we went for the triple bond, which is really the most important thing. So then we default back down to the next important thing to decide between which way of numbering. Other questions?
Okay, thank you.
You're welcome. Other questions on that? Okay. So oops, okay. Let's also do a couple here of names to formulas just to make sure. Let's do 4-propyl 2-heptene. And let's do 3,3-dimethyl 1-butene. All right, so take a couple of minutes here. You could do it's always good approach just again to work backwards from the name. So when we analyze the back part of the name here, we have heptene. The ENE tells me it's a double bond. The kind of hepta tells me it is 7 carbons. So that's really where I want to start. I don't want to really draw too much of anything else. Might as well just lay in the carbon backbone, if you will. So that's 5, 6, and 7. Again, the ENE means that there's a double bond. And where's the location of that double bond? It is at carbon number 2. So again, because you are drawing it, you could choose whichever way you want to number it. I'm going to go left to right, which means my carbon number 2 will be over here. So I'm going to put my double bond there. Again, carbon number 2 being right there. That takes care of that part of the name. Also, I see at carbon number 4, there's a propyl group. Again, important here because I decided that on the left-hand side here was carbon number 1. Next to it, obviously, would be carbon number 2, where I did the double bond. Next to that would be carbon number 3. And next to that would be carbon number 4. And that's where I would put my propyl group, which is a 3-carbon group there. That should take care of that. At this point, much like we talked about last time, everything else is going to be hydrogens. The goal here again is to get carbon to 4 bonds. So the guy at the end needs 3. Guy here needs 2. Guy here has 2 lines coming in, which means it needs 2 hydrogens. Guy here has actually 3 lines coming in, so just needs 1. The guy where the double bond is also has 3 lines coming in, so just needs 1. And guy on the other side, double bond, same thing. And guy at the end needs 3. Any questions on that? So taking the same approach here, the butane type part tells me it is 4 carbons. The YNE part tells me it's a triple bond located at carbon number 1. So again, I'm going to go left to right. So I'm going to call this first guy on the left there carbon number 1. Going to put my triple bond in there, and then that takes care of that. 3,3-dimethyl. So dimethyl means we have not one of these methyl groups in the compound, but 2 of these methyl groups. And where is each one located? Well, one is located at carbon number 3, and the other one is also located at carbon number 3. Again, because I chose this carbon on the left as carbon number 1, next to it would be carbon number 2, and next to that would be carbon number 3 here. At this point, that takes care of that part of the name. So what's left is hydrogen, so we're going to 3 hydrogen there. Carbon here actually has 4 bonds, so does not need any hydrogens. Carbon here with the triple bond actually has 4 bonds, does not need any hydrogens. Carbon at the very end needs just 1 hydrogen to go with those 3 bonds to get it to 4, and that would be our structure. Question on that there. All right, questions on how to name alkenes, alkynes. Obviously, you need to be able to do both of those things, go from name to formula or formula to name. Okay, so the next thing we're going to talk about then is cycloalkenes. So just like we have cycloalkanes, so if you remember our cycloalkanes were those kind of geometrical shapes like the triangle, the square, all those good guys, right? So we can have a double bond in here, and that makes it a cycloalkene. We kind of name it the same way. We put cyclo in front of it. We change the ANE to ENE. And in this case, though, because it's a ring structure, you don't have to give the location of where the double bond is located. It's assumed to always be carbon number 1. But if there are other groups attached, you do need to give its location. Now, there's an important thing when we have a double bond in a ring structure. And we have a group or something over here. When we go to number, we have an option as either this carbon is number 1 or this carbon here can be number 1. Now, when we're numbering to get the kind of location of this guy, there is an important rule that says we have to go through the double bond, which means if I want to number that group, I can't decide I want to go this way, like 1 and 2, because obviously I did not go through the double bond. So that would be an improper way of numbering. I would have to start here where that 1 is, and then go through the double bond to 2, to 3, to 4, to 5. And if I went sort of that counterclockwise way, again, through the double bond, that would tell me that this guy is at carbon number 5. My other option would be to start at the other end of that double bond and also go through the double bond. So starting here at 1 to 2 to 3 to 4 here, that would give me 4 in terms of my location. So just like anything else, we would want to choose 4 in this case, again, numbering 1, 2, 3, 4, 5, and 6. So it's important when you have a cycloalkene and you have some type of group attached that you do number, and you number through the double bond, not away from it, to make sure that you get the proper number in there. Any questions on that there? And that's what we see here with 3-methyl cyclopentane. This is a 5-member ring. 5-member ring with no double bond is cyclopentane. With the double bond becomes cyclopentane. Ene. Again, we don't need to give the location of where this bond is, but we assume that it is carbon number 1. So again, here, either carbon number 1 is here. We would have to go through the double bond to 2, to 3, to 4, to 5. Or we would have to do the opposite approach, which would be starting here at carbon number 1, going through the double bond to carbon number 2, and then down to carbon number 3. So clearly going sort of the counterclockwise or yellow direction does give our methyl group the smaller number, and that's why it is called 3-methyl cyclopentene rather than whatever that other way it was there, or 1, 2, 3, 4, 5, or 5-methyl cyclopentene. Any questions on that? Okay, so why don't you give these guys a go and see what you come up with in terms of the name. Maybe we'll add one more here. Let's do this one. All right, take a minute or two and see what you come up with. So if we count it up, there's basically 6 of them, I believe. 3, 4, 5, and 6. So that's a ring structure with 6 things attached. That is based off of cycloalkane, I didn't say that right, cyclohexane. There's a double bond, so then this would become cyclohexene, Ene. No need to give the location of this. This is assumed to be carbon number 1, wherever it's at. Again, there's no groups attached, so you don't have to worry about giving the location of that. Question on that name there. Coming to the guy on the right, we got 5, it looks like. 3, 4, and 5. So 5 in a row is cyclopentane with the double bond, becomes cyclopentene, Ene. Now we do have a couple of groups. Remember, we got some lines with nothing at the end. Remember, at the end, that means that there's a carbon and 3 hydrogens. These are methyl groups here, right? So we got like a dimethyl situation happening. And we need to figure out where these groups are in relationship to the double bond. Since the double bond is carbon number 1, we could go counterclockwise. 1, 2, again, going through the bond. 3, 4, 5. So that would put a group at 5 and 5. Now, if we went the other way, starting here at carbon 1, going through the bond clockwise, 2 and 3. So it does look like going sort of in the red direction there gives us 3, 3, which would obviously be a smaller number than 5. So putting all that together, 3, 3, remember, comma between 2 numbers, dash dimethyl, because there are 2 methyl groups in this compound, cyclopentene. And that is an Ene at the end there. Any questions on that name? All right, and then looking here at our square basically is 4. So that is going to be based off of cyclobutane, but becomes cyclobutene with the double bond. Again, our double bond doesn't need to be numbered, but it is going to be carbon 1, which gives us 2 options in terms of numbering. 1, 2, 3, and 4 gives us a group at carbon number 2 and a group at carbon number 4 in the red direction. If we go the other way, starting with our carbon number 1 at this end, 1 going through the double bond, 2, 3, and 4, looks like we end up with a 1 and a 3. Just like we talked about before, 1 is definitely less than 2. So we would want to go in the green direction, meaning that this is 1-methyl and that is 3-bromyl. The one that should come first is B before M. So we would actually have 3-bromyl, 1-methyl cyclobutene. Any question on that name? So we do go alphabetical regardless of number, as we saw the other day as well. So even though that's 3 and that's 1, alphabetically speaking, B before M. Any questions on the naming of cycloalkenes?
Can you write that one, please?
I'm sorry?
Can you write it out? Like how you did the other one? Oh, you did? Oh, okay, sorry. My bad.
Yep. This right here? Yeah. Okay. Yeah, so that is 3-bromyl, 1-methyl cyclobutene. Yep. Other questions? Okay, so we're then going to now talk about isomers again. We're going to talk about some different types of isomers that basically occur as a result of those double bonds that happen here with alkenes. So if you remember earlier, we talked about isomers, and again, isomers are the same molecular formula, but some type of different connectivity, if you will. And when we're talking about alkanes, which are single bonded, and you got some groups attached there, you know, whatever groups may attach, there is, because it's single bonded, what's referred to as free rotation around that bond, which means, you know, if you put the two carbons together, like in a model kit, you could spin it and the one carbon would just spin freely around and around with no problem, which is why when we draw, you know, an alkene or an alkane, you know, we could put the bromine to the right, we could put the bromine on the bottom, you know, I could write in this thing there. We could put the bromine, you know, on top and so forth. And it's because really there's that free sort of rotation that occurs. When we put a double bond into place, like we do with alkenes, it pretty much locks everybody in their place. So that double bond, when it comes in, basically will not allow the carbons to just freely rotate around the double bond. Because of that locking that occurs, what it ends up doing is it puts certain groups in different locations about that carbon-carbon double bond. You could have a group that ends up on the same side of the double bond. And that is what is known as cis isomer. It could be both groups are above it, could also be, you know, both groups are below the double bond. This would also be cis. You may lock into place where one group is above the double bond and one group is kind of below the double bond here. And this sort of opposite locations is what is referred to as the trans isomer, basically opposite sides of the double bond. So we do get this cis and trans isomers that develop. And again, it really is a result of that double bond really just locking everybody into place. You lose that really kind of free rotation that you have when it's just single bonds that are occurring. How do we know that a cis or trans isomer is really even possible? There's actually a couple of things you have to sort of make sure of in order to determine whether or not a cis or trans isomer is even possible. And or a cis and trans isomer to be possible, the first thing that you need to double check is when you look at the carbon in each of the double bonds, does it have two different groups? So for example, this carbon has group A attached to it and group B. A and B are different things, so that's good for it to be a cis or trans. You also need to do the same thing on the other carbon. You need to make sure that you have two different groups attached, which we do here as well in this made up example. We have group A on top, group D on the bottom, so attached to this carbon are two different groups. The second thing that you need to make sure of is when you look at the carbon-carbon double bond, are there two groups that are the same on opposite carbons? So are there two groups that are the same on opposite carbons? And in this case, there's an A on this carbon and an A on this carbon, which means that this would then be a cis isomer. So you do have to make sure, even for the possibility of cis or trans isomers to actually occur, you need to make sure that those two things are there. Do you have different groups attached to each carbon? And do you have a similar group on opposite carbons? And that was basically what allows us to figure out cis or trans. We oftentimes will add cis or trans to the name, as you can see here, cis or trans. They have exactly the same number of elements there, which is why they're isomers of each other. They're exactly the same. So if you look here, the two chlorines are on the same side, which is why this is cis. Chlorine is up on top, chlorine on the bottom, opposite sides of the double bond, which is why it's trans. But if we count it, we got two chlorines, two hydrogens, and two carbons, identically the same in each one in terms of what's there. But again, different three-dimensional arrangement, which is what makes them isomers. Any questions on that there? And again, here, it's as the thumbs show here, right? Thumbs on the same side, cis, thumbs on opposite sides, trans. Now, in a cis or trans, the alkyl groups are attached to the same side of the double bond, and the hydrogens are on the other side. In the trans, again, the alkyl groups are on opposite side. This is sort of a model view here. That's the CH3 group, and the two CH3 groups is really what that is on the same side of the double bond. Again here, CH3 group up, CH3 group down. Opposite sides are CH3s, which makes it the trans. Again, we do add sort of the prefix either cis or trans to the naming of it. And this is what it sort of looks like in line formula here. Double bond would be here. Again, the bromines are above. There would be hydrogens on the bottom. Here, again, double bond right there. We have one bromine above the double bond, one bromine below the double bond, gives us our cis and trans. Any question on those two? All right, why don't you take a second here and determine if this is cis or trans. I'll draw one more just so you could tell me. All right, so we'll add that one to this. So cis, trans, neither. Take a guess. I guess, hopefully. Okay, so obviously when we're looking at these, where do we want to focus in on? Well, we definitely want to focus in on the double bond, right, in each of these. All right, so looking at our double bond here, first off, we want to make sure this group and this group are different. This group and this group are different. And there are two groups that are the same. You could either look at the chlorines, which are on the same side, or the methyl groups, which are on the same side. They're both on the same side, which means that this guy here should be our cis isomer. Any questions on that one? Looking here at our double bond, the bromine and the methyl group here on the right-hand side are different. The methyl group and the bromine are different. Methyl group on opposite carbons are the same. Location, say, of the methyl group and the methyl group are opposite of each other, which means this guy would be a trans isomer. Looking at the last one here, again, hydrogen, which is considered a group in this case. Methyl, they are different. Methyl and hydrogen on the left-hand side are different, which is good. The group that's kind of the same on both is a methyl group. They are also on opposite sides. So this would be trans. Any question on those three? Looking here at this guy, the methyl group and the chlorine are different. So that's good. Coming to this one, though, chlorine and chlorine, that is the same. Which, because those are the same group on the same carbon in the double bond, no cis or trans could happen here because of that. So there would be no cis or trans isomer because it does not meet that qualification we talked about, eliminates the possibility of it occurring. Any questions on that one there?
Do you think that you can write the whole name for like one of them?
Yeah, I was just going to do that right now, actually. So let us actually talk about the name, which is an important thing, because sometimes when people sort of see it drawn in this sort of cis or trans sort of location here, they sort of mess up on what the name is. And it's understandable because what a lot of times people will focus in on is like the double bond. And they'll go, oh, when I'm going to name it, longest carbon chain here is going to be 2, because obviously that double bond is important here. And that really is not the longest continuous carbon chain. So you got to remember that even though it's drawn like this, if we were going to name this, we still want to apply our same sort of naming rules, which means we want to find the longest continuous carbon chain, which if we look at this one, that's 1 carbon, 2 carbons, 3 carbons, and down actually makes 4 carbons. So the base of this guy here would be butene, right? Because there's 4 carbons and a double bond. If we numbered this would be carbon 1, carbon 2, carbon 3, carbon 4, which means the groups here are actually 2 chloral groups at carbon 2 and 3. By the way, if you went the opposite way, you end up with the same numbers. So it doesn't really matter in this particular case. And that's at carbon 2 and 3, which means this would be 2,3-dichloral butene. Question on that name. This really would be cis 2,3-dichloral butene. Same thing if we look at the guy below it. 1 carbon here, coming down 2 carbons, coming over 3 carbons, coming over here 4 carbons. This is also butene, not ethene, because there's 2 carbons in the middle. This again would then be very similar name. That would be butene. Also at carbon 1, 2, 3, and 4. No matter which way you go, you end up with the same numbering. This would be trans 2,3-dibromal butene. Question on that one there. What would the last one be? Well, the last one would be 1 carbon, 2 carbons, 3 carbons, 4 carbons, and there really is no groups in terms of naming there. These hydrogens aren't considered groups in terms of the naming part. So this actually would just be trans 2-butene, 2 because the double bond located at carbon number 2. And by the way, I should have probably put that 2 in there as well. So my bad there. I'm sorry. Let me squeeze that in there. That should have the 2 on each of those names there as well. So let me just rewrite that real quick. Trans 2,3 dibromyl 2-butene. This guy would be 2,3 dichloryl 2-butene. We do need to get a location of the double bond. And this guy, I got the 2 here, I think, and that guy. So that's just be it. So yeah, I'm sorry. I should have the 2 squeezed in there. Other questions on that or naming of those guys? So very common, like I said, that sometimes people will mess up on the naming because they really will kind of focus in on the 2 carbons and end up calling, something like this, some dimethyls and dichloryls and ethene. But again, you still want to look for that longest continuous chain. You want to do better than I just did on those first 2 and make sure you put the 2 in there for the double bond location. And that's how you go about sort of drawing this. Now, if you had the name and you wanted to draw the structure, that too sometimes confuses people on sort of how to do that. So we just kind of clear that real quick. So let's just say we had the bottom name there, which was, actually we'll go with, I guess you can erase it. We'll go with this one, the trans. So again, I'll kind of cross that out so we got the right name there. Trans 2,3 dibromyl 2-butene. What is the best way to draw it to show cis or trans? Well, the best way to draw it is to actually probably draw it twice. The first way, you're just going to draw it like normal. And so butene would be, I'm going to lay up 4 carbons. Having the 2 there, which we should have, would be the double bond, would be at carbon number 2. 2,3 dibromal means at carbon 2, there is a bromine. At carbon 3, there is a bromine. And at this point, I'm actually just going to kind of put my hydrogens in. I'm going to actually, we need none here. So we'll go over here with my hydrogens. All right, so at this point, the way I drew it doesn't really show trans. It actually kind of shows cis, if you will. So what should you do? You should then redraw it by just focusing in on first the double bond. So if you refocus and just draw first the double bond there. And if you identify your groups, which is obviously a bromine, a methyl, a bromine, and a methyl, since I want trans, I could draw 1 bromine up, I could draw 1 bromine down, and then put the other guys in there as well. And now I have drawn it as trans, a little bit easier than just trying to go straight out and try to draw the trans as I'm drawing it. So sometimes it's beneficial if you have to draw these guys showing cis or trans, just draw it like normal, highlight the double bond, circle your 4 groups, and then redraw the double bond, and then orient your groups how you need it. If I needed it as cis, I would have put both bromines up. I need it as trans, I put them on opposite sides. So sometimes that's easier when you're dealing with trying to draw it showing the cis or trans. Any questions on cis or trans? Okay, so obviously you need to be able to identify things as cis or trans, need to be able to, draw these things and those type of things that you'll be asked to do. We're going to finish up here talking a little bit about the type of reactions that alkenes undergo. Alkenes and alkynes, they undergo what are referred to as addition reactions. So when we talk about addition reactions, there's really a general thing that occurs. So what occurs is we have, for the most part, a double bond, and we add something to it. Could be 2 things that are the same, could be 2 things that are different. But regardless of what you're adding to it, Unlike the substitution reaction, the same thing always happens in these reactions. And where does it happen? It happens right there at our functional group, right here. This is the only part of the molecule that will basically change. You could have 400 carbons to the left, 500 to the right. It's just going to be this spot right here that's going to change. That's an exaggeration probably. What's going to happen is in the addition reaction, what's going to happen is, for example, let's say that, we kind of completed this guy out correctly. All right, let's say we had ethene, which is what this would be, right? At this point, this carbon right here has 4 bonds. At this point, this carbon over here has 4 bonds. And as we know, 4 bonds is it. You can't put any more on there. So in order to make room for these guys, which are going to be added, we have to make room for it. And the way we make room for it is very simply our double bond becomes a single bond. Absolutely nothing else changes here other than you should, on the other side of the arrow, draw this exact same thing exactly the way it is and just turn your double bond into a single bond. Don't overthink it. That's exactly all you have to do, is draw this exactly like it is over there, just like I just did. And we're turning our double bond into a single bond. What does that do? Well, when we look to the guy to the right now, the carbon on the left has only 3 bonds. Carbon on the right has only 3 bonds. We have just made room for this guy and this guy to attach, which is why it's called an addition reaction. They're going to come in and attach. So what happens is one of those A's in my example, whatever A may be, will end up coming in on the one carbon where we made room for it. The other A, whatever it may be, will come in at the other carbon where we made room for it. We have just went from an alkene to a alkyne, alkane. I'll spit that out. There we go. In this sort of situation here. Any questions on that? Happens exactly the same way every single time, no matter how weird the molecule may look, no matter how many carbons there are. You simply need to find where the double bond is, redraw the molecule exactly the same, turn that double bond into a single bond, and add one thing to one carbon and the other guy to the other carbon. Happens just like that. Again, nothing weird happens like rings start forming, unicorns start flying, rainbows start appearing, nothing like that. We just simply break the double bond into a single bond to make room, and we add things in. Any questions on that there? So let's talk about a couple of different types of addition reactions, and there are a couple of different types of addition reactions. In alkenes and alkynes, the double and triple bonds are very reactive. And there's really kind of 2 types. And one is what is sometimes referred to as a symmetrical addition. And what does a symmetrical addition mean? Well, a symmetrical addition means like we add H2. That's basically adding 2 of the same things. Maybe we add Br2, which is 2 Brs, 2 of the same things. Maybe we add Cl2, which is 2 of the same things. So how would that work? Well, let's say we took we'll add an extra carbon to it. Why not? And let's say to this, we added H2 in this case, right? So this would be H2. what am I going to do? Well, I got a lot of carbons happening here. So as from our conversation just a second ago, pretty much know that that is where everything's going to take place. I also know that this is going to be an addition reaction, which means I can draw this guy exactly the same on the other side of the arrow. Again, the only thing we're going to do is turn the double bond into a single bond. Without thinking, just redraw it exactly the way it looks on the left-hand side, not thinking, just drawing, turning double bond into single bond. And I am pretty much 95% of the way there in terms of having the correct structure at this point. What did we just do? The same thing as we did before. We now have made room on the carbon on the right, and there's now room on the carbon on the left to do what? Add a hydrogen in each of these cases. So one hydrogen, which I'll just call, kind of make him green, will end up on one carbon. So we'll put him down here. We'll do a little highlighting of him so we could follow along where he ended up, right there. And the other hydrogen will end up on the other carbon. So we'll make him a different color. We'll go yellow. This hydrogen will end up over here on this carbon. And if we put that in there. Any questions on that? This addition is what is referred to as a symmetrical addition. It is known as a symmetrical addition because you really can't mess it up. You just need to put the same element on each carbon. So that's why it's known as symmetrical, because we're adding the exact same thing to each of the carbons. So again, that's what it means by symmetrical. Any questions on that one there? You sometimes will need catalysts, and you sometimes see these guys written on top of the arrow, like platinum, nickel, some other stuff. We do end up with a reaction which is sometimes referred to as a hydrogenation reaction. Why is it called a hydrogenation reaction? Because we added hydrogen. Yeah, that's why it's called a hydrogenation reaction. We'll talk about it a little bit later on in the class, but that's also what we get when we do. You get something that's known as partially hydrogenated, right? That's how they make like margarine and stuff like that, is basically by adding hydrogens, breaking some of these double bonds. There's another type of reaction that is basically what is referred to as unsymmetrical. And again, you could do this. This is not a hydrogenation reaction I'm writing right now, but you know, just again, show you that and one more down there. I feel like I got too many hydrogens there. I do. Get rid of that one there. There we go. So if we took this guy, and again, this is not a hydrogenation reaction, we're going to add a halogen here, Br2 basically. This is what's called a halogenation reaction, right? Because we're adding a halogen. Again, you may be looking at this and go, this must be really difficult because there's a lot more carbons happening here. But again, in this big giant molecule, that is the only thing that changes. And again, it changes the exact same way every single time. We're going to redraw it and simply make it into a single bond. So we're going to turn that double bond into a single bond. Absolutely everything else is identical to what we started with. Nothing else changes. It stays exactly the same. And now what we've done is what we were just talking about. We have now made room for one bromine to come in and the other bromine to come in. So a bromine would come here and a bromine would come here. Again, this being a symmetrical addition because we're adding the exact same thing. Any questions on that there? Yeah. So why don't you try one here and see what you come up with? Write the equation for the hydrogenation of 1-butene using a platinum catalyst. So let's just start with the 1-butene first, and I'll let you pick it up from that point. So butene, right, means that we have 4 carbons. 1-butene means we have a double bond there. Everything else is going to be hydrogens here. So we do 1 there, we do a couple there, and 3 there. Hydrogenation means that we're adding H2, which is 2 H's. Platinum catalyst has really nothing to do with any of the drawing part of it, but it would be up there on the arrow. All right, so now you take over and draw the product of what you end up with. You have to draw these things for these reactions to keep it as simple as possible. Again, people always want to do weird things, but remember, this is it. That's the only place it's going to change. We see this as a symmetrical addition, which means, you know, really almost without thinking about it, you should just copy exactly what you got going on here. So again, we're just going to copy it pretty much exactly. We're just going to change that one part, making it a single bond rather than a double bond. And again, as you can see here, absolutely positively, nothing else is changing. It's exactly the same. And again, the purpose of making that into a single bond is it now leaves a spot for a hydrogen to attach at each of those guys. And I'll just do it here in a different color so we can kind of make a distinction. We'll turn these guys bluish here. So 1 hydrogen will go where we made room over here, and the other hydrogen will go right about there. We again went from an alkene in this case to an alkane. Question on that? Okay. Now, as I was mentioning before, this hydrogenation reaction is sort of how we do get things like margarine, by kind of turning some of those double bonds into single bonds. It basically kind of softens things like butter and stuff like that into more of a margarine. Actually, the more single bonds that you have in these sort of fatty acids, which is what these are, the more like oil you sort of have. It's more liquid and stuff like that, or more solid at room temperature. All right, so why don't you take a second here and draw the product here of each of these. So let's take a look at it. And again, you know, you may want to redraw it just to visualize what's sort of happening here. Kind of expanded structural formula, you know, got this type of guy going. Plus H2, which is basically 2 hydrogens. Again, really the double bond, as we've been talking about, is the location. Going to redraw it exactly the same way, converting our double bond into a single bond. And again, like we've talked about before, what this now does is leave a spot at each of those carbons for our hydrogens to come in. Again, I'll put them as a different color so we can make the distinction. These are the guys coming in. That would obviously be the expanded formula. The condensed formula would then become this here, which is essentially we added a hydrogen there, broke the double bond. Any questions on that there? Okay. Looking at this guy, there's actually 1 hydrogen on each side of the double bond. Again, here, this ring structure, same deal. It is the double bond is the only thing that changes. It doesn't open up. It doesn't do anything weird. It stays the same, except we turn that double bond into a single bond. And now we actually have, although you don't usually draw it in this very badly drawn structure here, we have 2 hydrogens on each, basically hydrogen coming in from here and here, basically 2 hydrogens. question on those? Okay. So these are really symmetrical additions, adding two of the same things. Same general thing that you need to do. Make the double bond single bond, add one to one carbon that's coming in, add the other to the other carbon. Another type of reaction that occurs with our carbon-carbon double bonds is what is known as a hydration reaction. And a hydration reaction, hydration means water. We're basically adding water, and we can think of water as they have it drawn here as like a hydrogen and OH. So these are the two things that are going to come in as a result of this reaction. Is it going to be any different? It is not. This is what is referred to as an unsymmetrical addition. Unsymmetrical because we're adding two different things to our carbon-carbon double bond. You sometimes need an acid to catalyze it. So you'll sometimes see H plus up on top. You might even see H2SO4 on top. Has no effect on what you're doing. You will add it here. Now, when we do an unsymmetrical addition, when we add hydrogen and something else, I'll do that in just a second for you, okay? The hydrogen always ends up on the carbon where there is more hydrogens to begin with. So if there is sort of an option as to, you know, where you could put the hydrogen, the option would be that the hydrogen should end up at the carbon that started with the most hydrogens to begin with. May not always happen. I may not always have that option, but in some cases, that's what you do. The OH would go to the other. That's what's known as Markov-Nikod's rule. Basically, hydrogen goes to the one that has the most. This works for water. This also works for adding hydrogen halides like HBr, HCl. Works the same way. Hydrogen goes to one, halogen goes to the other. These are also unsymmetrical additions. So for example, here, if we look at this and we draw this guy out, just again to see the bonds. We're going to add H and OH, which is a weird way of writing water, basically. This is just a catalyst, speeds up the reaction, not going to do anything. You want to approach this in the exact same fashion as we did before. We're going to just make this double bond into a single bond. So what happens in this case, if I could get me a pen, maybe a different color. There we go. We're going to draw it identical to the way it was. So carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen, just like we did before. Now going to turn this into a single bond, carbon, hydrogen, and hydrogen. Now, we do have a little bit of analysis that we need to do in this case, because we're adding this unsymmetrical, which is we're going to add a hydrogen to one and an OH to the other. So Markov-Nikod's rule basically is the hydrogen should go to the carbon that started with the most. And what does that mean? It means you should go back here to our original guy. I could even do it in the one you're drawing. And attached directly to this carbon is one hydrogen. Attached directly to this carbon is 1 and 2 hydrogens. So this rule says that the hydrogen will end up at the carbon that started with the most, which means when we put that hydrogen on, it actually should end up at the carbon on the right-hand side. Because originally this guy started with 2 hydrogens, more than the 1 hydrogen that this guy started with, Where does the other guy come? The other guy comes to the other carbon, which would get the OH. This is what is known as an unsymmetrical addition. This is what is also known as the major product that would occur here. What would the minor product be? Well, the minor product would be you did it backwards, basically, and you would put the OH on the other one and the hydrogen on the wrong one here, sort of. So it would look like this. This would be the minor product, which is basically you did it opposite. You put the H here and the OH here. You should never draw the minor product. You should always go for the major product. So if you follow that rule, which is put the hydrogen on the one that started with the most, you will end up with the major product. Question on that there. All right, so to wrap up here, what happened is we actually went with an alkene. And what did we end up with? This is an OH group, which makes this a alcohol. So this is actually an alcohol. So a hydration of an alkene will produce an alcohol. And as a preview, this has 1, 2, 3, 4 carbons, which is 1 butene. The name of this guy would be 1, 2, 3, 4 carbons. And it has an OH group. This would be known as butanol, OL, because it's an alcohol. It would actually be known as 2-butanol because of the location of the OH group. So we'll talk about that obviously next time, but an alkene, adding water to it will produce an alcohol. And again, this is what is sometimes referred to as an unsymmetrical addition because you're adding two things that are different, unlike two hydrogens like we added before, or two Brs or two Cls here, a hydrogen and something else. Works the same way if it's not water, like I said. If it was like HBr, hydrogen would go to one, Br would go to the other, HCl, hydrogen to one, and Cl to the other. Any questions on that there? All right, we'll wrap that up today. We're pretty much almost done with this chapter. We'll roll into officially alcohols on Monday. And a reminder as well, we are having a quiz on Monday on chapter 9, which is solutions, since it's been a little while since we did that chapter, and it's going to be on the exam, just to make sure you remember that chapter. Don't forget about that chapter. So we'll have a lecture and we'll stop.